Okay, welcome everybody to the last talk of Devoxx 2019. For those of you coming in, there's still plenty of seats. People are holding up their hands if there are empty seats next to them. So this is the late 2019 edition of this talk. This is a talk that I revise continuously. I've adopted the Apple versioning numbering system. So this is the late 2019 edition of this talk. I've done similar talks before at Devoxx. Some of the material will be familiar. Some of it will be new. Don't buy anything based on what I say. So, okay. So, with a talk like this that has future in the title, one can give a talk about the future at any point in time because there always is a future. And in fact, I do give a talk about futures pretty much at any point in time. There's going to be some overlap year to year because a lot of the projects that we work on take more than a year to finish, and that's fine. But there's also progress from year to year. So if you've seen a previous version of this talk, some of what you see will be familiar, some of it will be new. So you can sort of think of this talk as a window in time, seeing multiple versions of this talk gives you a chance to gauge the rate of progress on the various things that we're working on. So time marches forward. Java is going to be 25 years old next year. And for a person that's still, pretty young, getting started in life, for a programming language, that's a little bit older. And certainly people have declared Java to be dead more times than I can count. But in reality, Java is still, by some measures, the world's most popular programming platform. And we want Java to continue to be vibrant and relevant for the next 25 years as well. And we have a super secret plan for doing that, which is to stay relevant. Stay relevant to the thing, as the world changes out from under us. Stay relevant to the problems that people want to solve using Java. Stay relevant to the hardware you want to run your programs on. Recognize that developer expectations don't stand still. So stay relevant to what developers expect their programming language to be like. And most importantly, keep the promises we've made to our users. Before I talk about the future, I want to talk a little bit about the past. And I'm going to talk about the fairly dim past, Java 5, which was basically 15 years ago. Java 5 was a huge release. It brought us generics and enums and the for each loop and autoboxing. And the reason I give this example is, it's easy to forget how much things have changed. So here's a program, here's a method you might have written in the pre-Java 5 days to add up a list of integers. We didn't have generics, right? So if you had a list of integers, all you could say was list. And you had to hope that what someone passed you was actually contained integers. And the way you got things out of a list is with iterators. So you grabbed an iterator, you iterated through the list, and you cast the result to an integer and added them up. And the dirty secret of Java 1.0, despite its claim of static typing, is that without generics, any non-trivial data structure effectively became dynamically typed because you couldn't put something into a collection and then have it come out and retain its type. You had to know what type you expect and cast it. And this makes code less readable and less reliable because there might be runtime errors. And this might not be a problem for a little tiny program, but it did present an impediment to programs growing above a certain size because there were all these implicits that were assumptions that were implicit in the code rather than being explicit in, say, method signatures. So what did Java 5 do for us here? Obviously, so how do you call this? You pass it a list of integers. Everything works great. If you try to pass it a list of things that weren't integers, the compiler says, okay, fine, that's a list. I'll take it. But then at runtime, you got a dynamic error. Not so much fun, right? And so in Java 5, you were able to say, no, what I want is a list of integers and get compile time type safety. And if you declare it that way, you didn't have to do the cast, great. Autoboxing meant that you didn't have to say .int value, it just automatically converted an integer to int, and okay, that was a big improvement. And if you tried to pass it a list of strings instead of a list of integers, you got an error at compile time instead of at runtime. And this makes our programs more reliable, right? Better static type checking. And there were also some productivity features in Java 5. We got rid of the iterator and added the for each loop. And so the code got simpler, easier to read, less accidental complexity, and more safe, right? So Java 5 was a big upgrade. There were, like I said, small productivity features, for each and autoboxing. Those are things that might show up in Project Amber today. But there were also big features for abstraction and type safety, namely generics. And then there was a huge effort to generify all the core libraries. How many people here started with Java before Java 5? Okay, so a lot of you remember those days, right? Have you ever gone back and looked at some code that you wrote in like 1999 and said, "Gah, how did I ever program like that?" I certainly have. The lack of static type safety just jumps off of the page at you when you look at it. Now, these features took a long time to do. Originally, generics were supposed to be there for Java 1.3, and they got delayed into 1.4 and delayed again into 5. And then once they were released, that wasn't the end, that was the beginning, right? It took a long time for people to adopt generics. A lot of libraries didn't adopt generics for almost 10 years because they wanted to retain compatibility with, with pre-Java 5 code. So Java evolution happens on a long time scale. Features take a long time to develop because it takes time to do them right, and it takes a long time to adopt them because there's a large ecosystem and a lot of code that has to be adapted. So it's essential that that adoption can be gradual. Migration compatibility is often one of the hardest things to get right in a language feature. It's certainly one of the things that made generics take such a long time to do, and it also is something that made that contributed to how long it took to do Lambda. So, jumping ahead in 10 years, Lambdas, Java 8, which gave us Lambdas and streams, was similarly a huge upgrade to Java. Just as generics in Java 5 gave us the better ability to abstract over types, Lambdas gave us ability to abstract over behavior. And, it got us out from under the pain of inner classes, but, that was sort of a minor benefit. The real benefit is Lambdas enabled a sort of a new breed of libraries, libraries like Java Util Stream. And sure, we could have written the streams library, or reactive libraries before we had Lambdas, but no one would want to use them. So we didn't bother, right? People probably did build these libraries, but they never got any traction because they were so painful to use because inner classes were so painful. So this sort of gives us a view of what we look for in language features and when we're designing language features. It's not so much that the feature itself is cool, although it may be, and it's not so much the the code that a given feature lets us write. The big benefit of a language feature, especially something like Lambdas, is what does it enable? We look at this as we're looking for leverage, right? If you improve the language, you want to make it easier to build better libraries, which in turn makes it easier to build applications. So the value chain is fairly indirect. Better language means better libraries means better programs. Okay, so I went and dug up this slide from one of my Java 8 presentations, and this was an example of code that was written in sort of pre-Java 8 idiomatic style, and which transformed into something much cleaner with the Streams API. Haven't touched this example since then, but again, looking back at that old example, which is now like only 5-6 years ago, it gives me that sort of like, God, did we really program like that? That was terrible. Okay, so before we look forward, let's draw a few lessons from our little look backwards. Big changes take time to get right. We could move faster, but there would be a bigger chance of getting them wrong, and that's worse because once you put a language feature in, it's very hard to take it away. And a bad feature is not something you can just ignore because it interacts with every other feature in the language. We talked about serialization yesterday morning as a great example of a feature that even if you don't use it, can cause problems for everything else. We also couldn't have survived either the transitions of Java 5 or Java 8 without a commitment to migration compatibility. It's just not acceptable to say to the Java community, okay, everyone stop what you're doing, we're going to have a flag day, everybody's going to recompile their code at once. That just would not fly, right? We have to make it possible for people to adopt these features at their own rate, which might be immediately, might be soon, might be later, might be never, and that has to be okay. Both of these features were also do or die features for Java. If we had gotten either generics or lambdas wrong, that could well have been fatal for Java. And on the other hand, you also can't believe the naysayers. Can't take them necessarily at their word, because people surely said generics are going to kill Java. People definitely said lambdas are going to kill Java. I mean, they even said local variable type inference is going to kill Java. And I guess this is just like fear manifesting as confidence, but you can't necessarily take the naysayers at their word. Okay, so looking ahead. How do we approach the features that we want to develop? Well, we know that languages have to evolve. If they don't evolve, they risk becoming irrelevant. On the other hand, if they move too quickly, we risk breaking our promises to our users. So we have to balance moving forward with compatibility. From our perspective, in the Java language, we view compatibility as not being an optional thing. We haven't broken our promises in 25 years, and that's why people continue to use Java. You really only get one chance to lose the trust, of your customers. So what that means is, sometimes there's a feature that we don't know how to do. We'd like to do it. We know what problem we want to solve, but we don't know what the right solution is. And the right thing to do in that case is wait until you do. Because, like I said, languages and features are forever. You have to pick and choose very carefully. Another way to think about this language features are forever thing is you don't want to do things today that you wouldn't want to be compatible with tomorrow. Right, so today, the features that we're adding today are tomorrow's compatibility constraints. So, if in doubt, we use as our guiding principle: does this make it easier to build and maintain reliable programs? Because that's really what it's about. Language features are cool, but they're just a means to an end. Okay, so how do we develop Java? We've changed this substantially in the last 2 years. Most of you have probably heard this by now, but about 2 years ago, we adopted a 6-month time-boxed release cycle rather than a multi-year feature-boxed release cycle. Features board the train when they're done. So we late bind to a release, and if they miss the train, oh well, there's another one in 6 months. It's not too long to wait. We test drive language features through a mechanism called preview. Preview feature is not, a half-baked experimental beta feature. It's a complete feature, but it's one that we might want to gather feedback on before we decide to make it permanent. So language features tend to go through a round or two of preview status before they become permanent. And for the bar for being a preview feature is pretty high. It has to be complete. It has to have, implementation, spec, library support, IDE support. But we reserve the right to, on the basis of feedback made by users, to make small changes. So they're good to experiment with. You probably don't want to run them in production, although you can. But the whole purpose of the preview mechanism is to get feedback, from people using it in real code. So there are a few features that are currently in preview now. Switch expressions, which were originally previewed in 12, and then re-previewed with a small syntactic change in 13, which we expect to make final in 14, which the engineering gate for 14 is closing in December. We also previewed feature text blocks, multi-line strings. In 13, we expect to be re-previewing that in 14, and hopefully that will be the last round of preview for that. So let's talk about these features. I've talked about these before. These are sort of half in the future and half in the past. And they're in the past in the sense that they were shipped as preview features, in 12 and 13, this one. But it may be in your future, because a lot of you are probably still not yet on Java 13, right? So this is sort of half future, half past. So switch. Everyone loves to hate switch. The switch construct in Java has a lot of oddities that were inherited from C. So, for example, fall through is the default. That was the wrong default, but we didn't know that in 1995. And that means you have to say break at the end of every, at the end every case arm. And the scoping rules are weird on top of that. So. Another strange thing about switch is it's a statement but not an expression, although if you look at real Java code, most uses of switch are simulating expressions, where you have in each arm, you're assigning some common target, and then you're going to use that target later. And whenever you're simulating one feature with another, it tends to be more verbose and more error-prone. So everyone's, when we started talking about this, everyone's first suggestion was, switch sucks, let's kill it, get rid of it, replace it with something better. I understand why people feel that way. It turns out it was better overall to rehabilitate switch rather than to try to replace it. And so, as part of the rehabilitation process, we addressed some of these issues. So now switch can be used either as a statement or an expression, and for well-behaved switches where there's sort of one action for each case, there's a way to write it that doesn't require any breaks or fall throughs. And so here's an example of that. This is the old way of doing it. I have an enum Monday, days of the week, Monday through Sunday, and I'm counting the letters. So I've covered all the cases, all 7 days are covered, and I use and I assign to this num letters variable in every arm, and then just out of perversity, the compiler forces me to include a default clause that if all goes well is never going to be reached. And so there's a lot of repetition here, right? I'm repeating the assignment. And I have to repeat these breaks, and that's kind of irritating. And like I said, the default clause, I have to write it even though, I hope it's never executed. So it's not, we don't enjoy writing code that we know is never supposed to be executed. So this is what that previous example looks like using a switch expression. So there's several syntactic changes here. One, you see switch used as an expression, which means you just assign the result of switch to something. We have streamlined syntax for multiple case labels, case A, B, C, and you see there's an arrow instead of a colon after the case labels, and that indicates that there should be one thing on the right side, and if it's a statement switch, it's one statement. If it's an expression switch, it's one expression, and if it's an expression switch, that becomes the value of the switch expression. Since expressions have to be total, the compiler will type check for us that we've covered all the cases. And in this particular case, it sees that the enum has been covered, so it doesn't force us to provide that do nothing default. It will actually generate one in the bytecode for us, just in case someone adds an 8th day of the week after I compile this program, but we don't have to deal with that explicitly in our code. So this is probably closer to the code that we wanted to write when we sat down to write the previous code, and now we can express it a little bit more directly. So the way this feature works is there's actually several changes that we've made to switch that are basically orthogonal. So one is statement versus expression. And if it's an expression, it does have to be exhaustive. The other is the form of the case label. So there's the old style case labels, which work exactly the same way they always did with fall through. And then there's the streamlined case label that has one consequence on the right side, which does not allow fall through. And you can mix and match these as you like. Most people will probably either stick to the old form or the expression form with the arrow labels, but you can mix and match them as you like. The original motivation for doing this feature was not better switches, although that was a nice outcome, but it was we were working on pattern matching, and we knew we were going to have to clean up switch to do pattern matching, and then we were able to sediment out some of these changes to stand on their own. Okay, so the other feature that's in preview now is text blocks. Everyone knows multi-line strings have always been painful in Java, but we want to represent multi-line strings all the time for snippets of JSON or XML or SQL or what have you. And the way, of course, we have to do this today is by manually cutting up the string into lines and then inserting the new line escapes. And that's annoying to do, and it's error-prone, and it makes it harder to read. And even if the IDE does the mangling for you, it's still harder to read. So a text block, we spent a lot of time trying to find the right name for this feature, which you'd think is silly, but actually makes a difference. Multi-line string didn't feel evocative enough because the feature that we ended up doing is not just a string that spans multiple lines, but it's really a two-dimensional string literal. Yes, it can span multiple lines, but it's also the case that the lines are intended to be indented relative to each other. So you can think of it as a block of text. And then, since we're embedding this in our source files that already has indentation for the way we indent our code, the compiler is going to try to figure out which indentation is incidental and which is desirable, and strip away the incidental part. So here's how we write a multi-line string today, and here's how we write it with a text block. Not particularly exciting, different delimiter, spans multiple lines, doesn't have to have those escape characters. But the thing that's more interesting is how we handle the white space. So now there's all of this white space, up to where like HTML starts. And that is all incidental indentation. We put that in to line up our program neatly because programs are for humans to read. We don't really want that space to be part of the resulting string. And so, the compiler uses a heuristic, it's fairly well documented one, to say, all right, well, I think this space, the ones indicated by the dots, are incidental, and I'm going to trim those away. But these lines are indented relative to each other, so wherever the HTML line starts, the body line is going to start 4 characters in. And there are ways to adjust how the compiler does this, but the basic essence is, imagine there's this magic rectangle that in your code that delimits the actual block of text you want, and the compiler goes and figures that out. And that way, if your IDE re-indents your code, it's not adding extra spaces to these literals. So, sort of an interesting development story. During the development of this feature, the design center actually shifted twice. First, we thought the design center should have been raw strings. That turned out to be a mistake. It was a well-intentioned mistake, but it was a mistake. And we shifted the design center to multi-line strings, and then we shifted again from multi-lineness to two-dimensionality. These shifts were informed not only by thinking about the problem, but also by analyzing bodies of source code and looking at what people use multi-line strings for. So, okay, those are the features that are in preview now. I want to start talking about some features that are coming that we hope to be previewing soon. So the next one I'm going to talk about is records. This is one that we hope to preview in 14. Not guaranteed. It could slip out of 14 into 15, but we're still pushing at it. So we hope it's going to get in. I've talked about records before, but now I get to talk about the feature that we're actually going to deliver, as opposed to the feature that we would like to deliver someday in the future. So, records are addressing a common problem that Java developers have, which is classes that are just wrappers for their data. And we all know how to do this. We've all read Effective Java. We know how to model data as objects. We do it with lots of boilerplate, right? Constructors and accessors and equals and hash code and toString and all of that. And these aren't fun to write. And even if the IDE generates them for us, they're still not fun to read. And it's not just about fun. It's, when repetition is a place for bugs to hide. If you have code that is low-value boilerplate code, you still have to read it to convince yourself that there's nothing there to read. And, so you do all this work to read the code, and your reward is, oh yeah, I didn't have to read that. We would like it to be the code you don't have to read actually doesn't have to be read. Okay, so running example, like I said earlier this morning, I only know how to write one class, so it's XY point. And we'd like to write just, point int x and y, but we have to write a constructor, and we have to write an equals, and we have to write hash code, and we have to write toString, and we have to write accessors. And that's all very disappointing, because the semantic content of this class is really a point, has an int x and an int y, I'm done, right? So, not all classes can be described this way, but a lot of them can, and we all write them every day. So what we like to be able to say is point is a record. It has components, int x, int y, And that's all it has. And what this is not just a syntactic improvement. It obviously is a syntactic improvement, but there's something deeper going on. What you're saying is the class point is the tuple int x int y. And that means I can mechanically derive my API, my construction API, deconstruction API, access API, semantics of equality and hash code from this state description. And the compiler can reason about that, and frameworks can reason about it. If you look at like code that we write today that does this, where you see there's a field called x and a constructor argument called x and a getter called getx, it's kind of this big leap of faith that they're all talking about the same x. Right? And one of the reasons we end up with all this boilerplate is there's no way to talk about these things at a higher level. So records are actually a higher level description of, here's a class whose representation and its API are coupled in this very predictable way. So what is a record? You can think of a record as a transparent, meaning you can see its data, shallowly immutable, which is to say its fields are final, data aggregate. Or the data, the whole data, and nothing but the data. The way I like to think about records is they are nominal tuples. So the aggregate has a name, point. The components have names, x and y. And this is a trick that we've pulled before, right? If you look back to Java 8 when we did lambdas, and we talked about the type of a lambda expression, everyone's first thought was, let's add structural function types to Java, function from int to int. But because of the way things have been done in Java for the previous 20 years, we chose to do something differently. We used nominal function types, functional interfaces. We used interfaces with one method to describe the shape of a lambda. So we made a choice to do nominal function types over structural ones. Records are making the same choice for tuples. We're doing nominal tuples rather than structural tuples. Now, this is not a feature without controversy. Everyone had opinions on what records should be. It was kind of funny. Everyone agreed that they liked the feature. Everyone agreed they liked the concision, but very few people agreed on the goal. And so surely there will be some people who wish we would have done it differently, because you can't be all things to all people. But like I said, it's better to think about this as a semantic feature than a boilerplate reduction feature. Surely they give us the boilerplate reduction, but they're not really about the boilerplate. They're about making a straightforward statement that this class is a carrier for this data. And this kind of semantic statement is very similar to the trick that we did with the enums in Java 5. So enums, when you say enum instead of class, you're making a statement in which you're giving up some control. You're saying, I'm giving up the ability to control the instance of this class. And in return, the compiler generates a lot of boilerplate for you that you don't have to do yourself. So you gave up some control, you got some functionality in return. And records do the same thing. What you're giving up is the ability to decouple the API from the representation. And in return, what you get is sensible defaults for constructors, accessors, equals hash code, toString, all of that. And so our approach here is that if you get the semantics right, the boilerplate will take care of itself. That very rarely works in the other direction if you start with boilerplate first. There's kind of another hidden benefit here, and it's one we saw with local variable type inference as well. By reducing the overhead of declaring a class that does actually what you want it to do, it reduces our incentive to be lazy and cut corners, and this results in better code. We saw this with local variable type inference. By reducing the overhead of declaring a local variable, we were more likely to pull a common sub-expression out and put it in a local and give it a name, because we didn't have to pay this penalty of typing this big ugly type in order to declare a local variable. And I think that pushes us to writing simpler code that isn't so heavily, doesn't rely so heavily on nesting and chaining. And I think the same thing will be true with APIs with records. So, okay, what can I do with them? Well, they're classes. They can have almost all the things classes can have. So they can have methods. I can, you get a certain number of methods for free. You get equals and hash code and toString for free, but you can have more. So here's an example of, computing the norm of a point, square root of x squared plus y squared. You can declare constructors explicitly so that you can get argument validation. If I have a record that describes a range, I'd like to make sure that the low end of the range is not above the high end of the range. So I can declare a constructor. I got a constructor for default, by default, that just initialized the fields. But I'd like to have a constructor that checks the invariant. That if low is greater than high, then throw an exception. But this is a little bit unfortunate because we wanted our records to be nice and compact, but when I went and added my constructor, I had to add back some boilerplate, right? I had to redeclare the constructor arguments, and I had to reinitialize all of the fields from the arguments. And so records also have a more compact way of declaring a constructor, where you leave out the argument list because it knows what it is. It's the one right above it in the class. And it will fill in the initialization of the fields from the arguments. And so all the constructor has to do is the stuff that needs to be explicit, the invariant checking or the argument normalization that the compiler can't know what you want to do. And then all of the dumb stuff just gets filled in automatically. So they're classes. You can add methods. You can add constructors. Let's look at a few quick use cases. It's not hard to imagine how this is useful. Here's the kind of API that we tend to write without something like this. You want to be able to compute the minimum and maximum over some collection, so you have methods that are generic in T, takes a collection of T or iterable of T and a comparator of T, and hands you up the minimal and maximal values. Well, it's generally more efficient if you're looking for both of these to compute both of these at once. So you only have to iterate through your elements once and pull them into cache once. Why didn't we write it this way? Well, there's a good chance we didn't write it this way because there isn't a convenient way to return two things at once, and we're too lazy to write a big class just to hold these two values. So I can declare a record. Records can be generic. They can have type variables. So I can declare a record with one line saying min-max is a holder for min and max, and then I can have my method return that. Right? This is one of those lowering the overhead of a declaration makes it more likely we're going to write the correct API. And some of you are probably saying, well, if the language had tuples, I wouldn't even have to write that first line. And you're right about that. And, but part of the philosophy of the Java language is names matter. Calling this min-max, calling the components min and max rather than first and second, makes the code more readable. When somebody calls this method and is, accessing the min or max, components, it's much more obvious what's going on than if they're just accessing first or second. So names matter, nominal tuples. Okay, another example of how this might be used. A common question on Stack Overflow about the Streams API is, supposing I have a stream of some object, say a stream of person, and I want to sort it by some derived property that I don't happen to have materialized, and I don't want to compute it for every comparison because I'd have to compute it O of n squared times, and that would be wasteful. How do I, how do I do that? So in this example, I want to compute, the top n people by a certain score, and the net, I would like to do that by, using streams, saying sort it, limit it, return the top few. But I want to sort of carry around this extra bit of data. And so I can implement that quite conveniently by saying, okay, declare a record to hold the tuple of a person and that person's score, and then take my list, turn it into a stream, map the person to the tuple by computing the score once per person, and then sort by the score component, take the top n, and then map it back to the person component, throwing away the wrapping tuple, and collect those to a list. So this is something that's a little trickier to do. Without a mechanism like this, people do silly things with two-element arrays and things like that, which makes the code less readable. But the notable thing about what's going on in this example is this record is local. It's not polluting your program's namespace. It only serves this method. So that's fine. Just like Java has had local classes since the 1.1, most of us don't use them very often, but they are pretty useful, and local records are really quite useful. There are lots of other use cases. any kind of tree node or document node, data transfer objects that we're passing between layers, compound map keys. We've all written a class for a compound map key over many times. We probably all grumbled while we were writing it. Messages in message passing and actor-based systems. There are so many uses for this. So it's the sort of thing that I suspect that in a few years we'll be saying, how do we live without that one also? Okay, let me talk about another feature that is likely not to make 14, but I hope makes 15. Hope, not promise, hope. And it's related to records. Records are, another word for records are algebraic product types. So if we were programming in ML, we would call them products. And they're called products because their state space is the Cartesian product of the state space of their components. Languages that have product types also usually have sum types. What are sum types? Sum types are discriminated unions. It's a way of saying this thing is either A or B or C or nothing else. So for example, a shape is a circle or a rectangle, and those are the only two kinds of shapes. That's useful because it lets the compiler reason about exhaustiveness, that if you've handled the case for circle and you've handled the case for rectangle, then the compiler knows you've handled all the shapes. Sealed type means basically it can only be extended by a specific list of types. In particular, sealed types whose leaf types are records is a particularly useful combination. This also is really useful for us in the platform because it allows us to expose interfaces and use polymorphism, but control all the implementations, which means that we can implement them more efficiently while remaining secure. Okay, so here's an example of a combination of records and sealed types. So I have our point record that we had before, and we say shape is an interface, and it's a sealed interface, and it explicitly lists the subtypes that are allowed to extend it. Shape permits circle and rect. Well, circle and rect are classes, so we can declare those as classes, or we can declare those as records, because records are classes. And we say, so we'll use records here, and we'll say a circle has a center point and a radius. And a rectangle has a lower left and an upper right bounding point. And these are the implementations of shape. So not only have we declared this more concisely, but the compiler can give us better type checking because it knows that the only subtypes of shape are circle and rectangle. Okay, so why, right? What's the point? A lot of people look at this and say, this didn't seem like a feature I thought I needed. But how many people here have written a final class? Did you have a reason for it? You probably did, right? Otherwise you wouldn't have done it. Sealing is a generalization of finality. So many of the things that are useful about final classes are also useful about sealed classes. It means you can expose them to be used but not subclassed. So libraries can expose abstract data types as interfaces, but still control all the implementations. And the compiler can reason about exhaustiveness. It can reason about whether all the cases are covered and provide code with better compile time type safety. We see patterns that use sealed types all the time, where we want to say, this is either something that looks like this or something that looks like that. For example, if you were writing a library for asynchronous computation and you want to describe the result of a computation, it's either a timeout or it's an error, in which case it has a data parameter, which is an exception, or it was success, in which case it has a result. Being able to define a type like this, that is either this or that or the other thing and nothing else, fits very nicely into the next feature I'm going to talk about called pattern matching. Okay, so pattern matching is a feature that if you've seen before, you've more likely seen it in functional languages. We've been working on it for quite a while. We hope to get the first phase of it into 14 as a preview feature. The essence of pattern matching is there's something we do every day, which is code that combines doing a test and a conditional extraction. And we do these things together all the time. So as an example, take instance of, we ask, are you an instance of integer? And then what's the next thing we do? We cast it to integer. And then we bind the result to a local variable, and then we use that result. So this is, unnecessarily repetitive. We had to say integer twice. That's minorly irritating. But more importantly, the cast is error prone, right? We just tested it. The next thing we do after an instance of test is always a cast. The only thing we can do there is accidentally get it wrong and cast it to the wrong type because we cut and paste from somewhere else, right? So that's, repetition is a place where bugs hide, right? This is an opportunity for bugs to hide. Some languages address this with flow typing, but I think pattern matching is a much richer answer. So a pattern fuses three things: a test, an extraction that is only done if the test succeeded, and binding the result of the extraction to fresh variables. The first place we're going to expose pattern matching, that's what's coming hopefully in 14, is type patterns in instance of. And a type pattern is just a type name and a variable name. Looks like a declaration, not an accident. And you can put one of these things on the right side of instance of. And so the previous code, which was if object instance of integer, becomes if object instance of integer and then a variable name. And what that means is test if it's an integer, if so, cast it to integer and bind the result to this fresh variable, and then you can use that in the code. So that's nice, less boilerplate, fewer places for bugs to hide. There are, this is a very, very simple use of patterns. There are other kinds of patterns and other places that we can use them that will be coming in the future. So we started simple with type patterns in instance of. The nice side effect of that is basically every cast disappears because the compiler can figure out that, well, of course the next thing you're going to do is cast it to that type. It also works very nicely with Boolean ands, which this question came up on Twitter this morning. Someone was asking about this, where isn't it, if you look at the code that most IDEs generate when you say make me an equals method, isn't that code ugly, right? It has nasty control flow. It's hard to follow. If we rewrite this using pattern matching, it gets much cleaner because the scoping of the variables flow very cleanly. So if we say, if O instance of this class and we bind it to something, we can then use that name in the expressions that follow. So if the other thing is the right class and my size equals his size and my name equals his name, then the two things are equal. This is a much easier to read implementation of equals than the thing that your IDE was going to generate for you. It's also safe. The compiler makes sure that you only use the binding variables where they are definitely assigned. So looking ahead, we can use patterns in other places too. Here's an example of some code that we unfortunately have to write a lot, where you say, is something an instance of integer, is something an instance of a byte, and in each case, you ask the question and then you cast it. And you're asking the question over and over again, and you're likely doing the same thing in each of those branches. And if we allow to use patterns in case labels, we can eliminate the casting, so that's helpful. The code is starting to get a little bit clearer. And if we combine it with the expression switch that we saw before, the code gets a lot clearer indeed, right? That is much less accidental control flow, and it's much more obviously what you're trying to do here. So patterns fit naturally with instance of, they fit naturally with switch, they fit into other places as well, and over time we'll see more of them. Patterns have a natural connection to records also, because earlier I said that records are transparent. They give up their state. So that means they're amenable to deconstruction. And in the future, not this next version, you'll be able to use pattern matching to deconstruct records, and the pattern will automatically be available for records in the same way that the constructor and accessor and equals and toString are. So the way to read this code, the thing on the right is a pattern. The pattern matches anything whose type is circle, and when it matches, it gets the center component and the radius component and binds them to those declared variables. So combination of a type test, a cast, extraction of the components, and binding them to variables. Now, you might be wondering, well, how does it find the center and the radius? It's not doing any of the ugly things you're imagining. It's not doing like magic field scraping or anything like that. This deconstruction pattern is just code. It's like the opposite of a constructor. A constructor is code that takes a bunch of state components and aggregates them into an object. A deconstruction pattern takes an object and explodes it into its components. So pattern matching also connects very nicely with sealed types. Even though we're delivering these as separate features, they work together very nicely. So continuing with the sealed type example, if I want to compute the area of a shape, I can switch over the shape, and one of my cases can be a case for circle, which is a deconstruction pattern for the circle record, which automatically extracts the components I need, so I can just compute pi r squared without any extra ceremony. And similarly, for rectangle, it's going to extract the lower left and upper right points, and I can compute delta y times delta x. And because I know that shape is a sealed type, and I've covered all the circles and all the rectangles, the compiler is not going to make me say a default. So writing this code without these mechanisms would be not only more code, but more error prone. So these are features that work very nicely together. So we will see records coming first, pattern matching with type tests an instance of first, and then we'll be adding in different kinds of patterns in different places where we can put patterns. So a few minutes left, let me sum up. Our feature pipeline is pretty amazing. There's more, there's so much more that we want to deliver. We'd like to deliver faster. This year has been a really productive year. The significant batch of features from Project Amber are starting to show up. I've been talking about them for a while as things we are working on. They are now things that we are ready to deliver, and there's lots more coming. I didn't get a chance to talk about Valhalla or Panama at all. That's not because these haven't made amazing progress in the last year. It's that there was so much good stuff coming from Amber that's all I had time to talk about. So it's been, a pretty amazing year, and I think there's an awful lot of good stuff coming. So with that, we have about 5 minutes for questions, and they might let us stay a few minutes late because it's the last session of the day. So question over here. Yep. Okay, so the question is, how is trailing whitespace handled with text blocks? And by default, it's stripped. If you don't want to strip it, there are tricks you can do to say, no, I meant that, keep that. So, question over here.
Will the deconstructor allow something like underscore for fields you don't care about?
So the question is, will we support wildcard patterns so that we don't have to bind a name to fields we don't care about? Probably. We haven't quite decided how we want to surface that, but it's a obvious thing to want to do, and it's trivially easy to do. So we will probably do some form of that. Not sure it'll be underscore, but it might be. Questions? Question over here. What are the implications on compilation time? Negligible. None of these features require an awful lot of computation. When we get deeper into pattern matching, it's conceivable that exhaustiveness, if you have a very complicated switch with deeply nested patterns, there might be more work to compute exhaustiveness. But these are relatively cheap features to compile.
Brian, is Val committed a Java?
What's that?
VAL. Is Val. You've got VAR.
Yeah.
Is Val committed to the language?
No. Answer hasn't changed in 2 years. No. All right. Who else has a question? Mario.
How records are related with value types?
How are records related to value types? Fantastic question. Thank you. You might think that records and value types are almost the same feature, because they're both data aggregates, and they both force your fields to be final. These are sort of accidental similarities. So value types are classes that don't have identity. So it's another one of those trades of I give up identity and I get a bunch of benefits, largely having to do with memory layout, flatness, density, etc. records, what you're giving up is flexibility to decouple your API from your representation. And you get a certain set of benefits from that. Mostly, you get certain members for free. If you're willing to give up both of those things, you can get both of those benefits. And you can have an inline record. And the two of them compose in a fairly clean way. But they're not the same thing. Yes?
Types and pattern matching play with separate compilation?
Okay, so the question is separate compilation. When we did enums in 5, we made a deliberate decision to not use the exhaustiveness information that was present in the enum because someone might add an 8th day of the week, right? That was I would call that an abundance of caution. Where that decision came from. So when we're talking about doing the same thing with sealed types, where you're introducing a similar kind of exhaustiveness mechanism, we looked at code that people had written, and one of the things we discovered is the default clauses that people write throw very uninformative exceptions because they're already annoyed that they have to do it at all. And in fact, the compiler can throw a much more informative exception in the case of separate compilation. And so we decided to change our perspective and say, yes, we understand that this could change under separate compilation. We have a story for that. The compiler will generate a default clause so that if at runtime a novel value shows up, you'll get a well-behaved exception. There's a second benefit to this as well, which is if you have a default clause that throws and someone adds a new enum, you don't get any memo that says, hey, you're switching over this thing that has a new value, maybe you want to change your code. Whereas if you leave the default out because you were exhaustive, if someone adds another enum or another sealed type member, the next time you go to recompile that code, it won't compile. And now you have a choice. Do I want to sweep it under the rug with a default clause, or do I want to handle it directly? So I think it's actually less error-prone to have the compiler infer the default clause on a total switch than to make the programmer write it. So long answer to a short question. I think we can take one or two more. Are we okay on time? Yeah. All right, we'll take one or two more, and then we'll break. I saw a bunch of hands going up before. Right over there, sir. Yes, so the question is, so it seems like you're generating equals and hash code for records, and presumably the equals and hash codes are derived from the totality of the state, which they are. Can we use those as map keys? Yes, absolutely. That's a great use case because now you have a well-behaved equality and hash code without having to declare it. So very often people try to avoid doing this for compound map keys and often write error-prone code. So this makes it much easier to do the right thing.
Are they comparable?
The question is, are they comparable? No, but you can say implements comparable and write a compare to method because it's a class. They can implement interfaces, they can have methods. Okay, one more question.
This guy up there?
I can't see anything.
Upper left.
Upper left, yes, in the front row of the balcony. So the question is, in a record, can you control which attributes go into the hash code? Yes, all of them. But if you insist, you can declare a hash code method explicitly and do what you want. You should ask yourself whether that's what your clients will expect, but you can do that. You can declare equals and hash code explicitly and do whatever you want. There is an invariant in the specification for records. There's just like enum, there's a superclass Java-lang enum that's a supertype of all enum classes. There's a similar one record that's a supertype of all record classes. And in that class, it says that you should be able to take the components of a record by calling their accessors, feed them back to the constructor, and get something that is dot equals to the thing you started with. So if you override equals or hash code or the constructor, you need to make sure you override them in a way that's consistent. So that means if you override equals, you might also have to override the constructor. But you can do it. All right, so I think that's it for this year's Devoxx. Thank you very much. We'll see you next year.